evening, which is we're going to talk a bit about what are called linear Diophantine equations and how to solve them. And so this is a bit of strange terminology with this idea of Diophantine equations, because it's not really a certain type of equation so much as the kind of solutions you're looking for. So when people talk about solving Diophantine equations, the equations themselves will just look like any other equations you might have seen, but what the idea here is the solutions that you're looking for are supposed to be integers. Okay, so the point here is we look for integer solutions. As opposed to just solutions that are maybe real numbers or something else. So anyway, the start here for us in this, in fact, pretty much all we're going to do in this chapter, is look at equations like this. So things like ax plus by is equal to c. And that's the title of this next section. So in this kind of an equation, a, b, and c are supposed to be given integers, and x and y are like the variables. And the business is trying to find x and y that satisfy a linear equation like this, but specifically we'll be talking about the integer solutions. Okay, so anyway, this ax, okay, so the situation is, right, so given integers, a, b, and c, what we are looking for is we are going to be interested in integers, well, integer pairs, I guess, x comma y, that satisfy this equation. This is what's called a linear Diophantine equation. Anyway, it's just a linear equation. It's again, Diophantine is sort of just saying it's the state of mind you're in, like in terms of what kind of solutions you're after. Now, I mean, if somebody said, let's not talk about integers, but let's talk about real numbers, pairs of real numbers, x, y, that satisfy this equation, these things make a line in the plane. Like you know this for a long time. The graph of this is a line. But we're interested in essentially the points on such a line that have both coordinates being integers. Okay, so anyway, we're going to learn how to describe them all. And we could ease our way into this story by looking at some examples, which will touch upon some things we've learned already. So here's one example. Now, okay. Actually, before I give the example, let me just give us the goal, the eventual goal. Let's say the goal will be to find or to describe all such solutions. Okay, now, right now with the example I wanted us to start with, we're not going to describe all of them, but we're going to at least describe one. Okay, so here is an example to consider. So suppose we wanted to find integers x and y, which satisfy this thing. Okay, let's back off the word all here. Like, let's not worry about the whole family of possibilities. But if we just wanted to find one pair of x and y that satisfy this equation, in fact, we've already done this in this class. So the thing is, these two integers, 19 and 7, are relatively prime. That makes their GCD 1. And this is really just like asking us to write 1 as a linear combination of 19 and 7. we actually did this specific example already. So, but the point was, I guess, this kind of a thing, you can find one solution to such a thing via the extended Euclidean algorithm. Okay, that's what this is really about here. And that's a thing we've done before. And let me just mention the solution we found, but by the extended Euclidean algorithm. And this was actually an example we already computed, so I'll just write this down. We found in the past 19 times 3 plus 7 times -8 worked out to be 1. And so that gives us one solution to the equation. Okay, so having x be 3 and y be -8, this is one solution. Okay, and so the point of this example so far is that this extended Euclidean algorithm is probably going to help us out. It's going to play a role here. Okay, that's one solution. I said, let's back off this all word for a second. We'll come back to that later. But that's one. There are, in fact, more. Okay, but this kind of a thing can be built on in the following way. So let me show you a slightly trickier example. Okay, so for a different example, what if you wanted to find integers x and y? Which satisfy this equation. So let me keep the left-hand side the same, but make it something else on the right. Let's make it 6. Okay. So say we wanted to do this. Now, it's not directly. I mean, the extended Euclidean algorithm will tell you how to write 1 as a linear combination of these two numbers, and 1 is the GCD and 6 is not the GCD. So it might sound like that's not helpful, but in fact it is quite helpful still. So here's the thing. We know this thing over here, right? We do know this. And the problem is we have, in this equation, is there's a 1 on the right instead of a 6. Okay, but look, there's something really simple you could do to this equation, which is you can multiply both sides of the equation by 6. Right? That would put a 6 over here. And when you multiply these terms by 6, you could just kind of absorb that 6 into these coefficients, right? And then this essentially gives a solution. So this can be found by multiplying both sides of that equation we had over there. So what was this? We had 19 times 3 plus 7 times -8 equals 1. You can multiply both sides by the number 6. And what does this get you? It gives you that. Okay, so when we multiply these things by 6, we'll just take the coefficients times 6. So 3 times 6 is 18. And then -8 times 6 is -48. And then over here, 1 times 6 is 6. So evidently that must be true. And that would then give us one solution, right? So I mentioned it before. There are more. We'll talk about how to find them later. Okay, but this is a really useful thing. It's going to play a big role for us. And so in this kind of an example, what you would realize is that if we could change this right-hand side to be any integer we want. If we wanted to find one solution to this equation, we could just do this. Right? Nothing special about 6. It could have been any other integer, and that little trick would have worked. Okay, so that's going to be a useful method for us. Okay, but there is one more example I'd like to show you. Something a little different. Change some of those coefficients around. Okay, so what if you now wanted to find integers x and y with the following property? So the equation here will be 6x plus 15y is equal to 10. you think about this one? Thoughts? Yeah.
We find the GCD of 6 and 15 and then just apply the same thing over again?
Well, we could, but what is?
Oh, I don't know.
I mean, you could tell me. Can you tell me the GCD of 6 and 15?
3.
3. Okay. Well, how would that work then? If you tried to do this, right? Well, you might have a situation. Yeah.
You can find the GCD, and then because it's the GCD, you can basically divide both sides by the GCD to get them equal to 1, and then you can just multiply by 10.
Well, there's a little bit of a problem with the right-hand side, though, right? So, I mean, like if you're thinking about dividing, like first of all, their GCD is 3. I mean, something you could think about is dividing both sides of the equation by 3, but then what happens over here is you're not in the integer world anymore.
Oh, I meant like you do Euclid's, so then you get like the summation of like some number times 6 plus some number times 15 is equal to 3.
Yeah, like something like this, right?
Yeah.
Okay, then what do you do?
And then you know both sides are divisible by 3, because one of them is 3 and the other one, their GCD of the two is 3. So you know you can divide by 3. Like,
I love it.
both sides.
Now this?
Yeah,
Yeah,
because
you
you
can do
know,
that. But how's it going to help you?
because then you get 1, and then you're back to the original example.
Yeah, but you change the numbers, right? So then you have like,
Oh, okay.
then you have 2 and 5 instead of 6 and 15.
Yeah.
Right, so, look, we're so close. Well, but there's, look, what would happen, right? So I have this, if you tried, let me just say, what if you tried to do exactly what we just did, but now you're starting with this, and you say, oh, I'll just scale it up to get a 10 over here. Okay, there's a problem, because if you want to scale this up to be a 10, you have to multiply both sides by 10/3. And you can't just kind of suck that into these coefficients here, because then they're not integers anymore, and now you have a big problem. Okay, there is in fact a problem, and let me point it out to you quite clearly once you see it. Once you see the problem very clearly, you say, oh, of course. Look, the GCD of these numbers is 3. They are multiples of 3. The left-hand side of this equation is a multiple of 3. Agree? Okay, is the right-hand side a multiple of 3? No. Okay, well that's a problem, right? So look, if x and y are integers, left-hand side is divisible by 3. But the right-hand side is not at all divisible by 3, and that would be contradictory. So this is actually impossible to satisfy. There are no integers x and y to make this true. Okay, so that's the point. So look, this is an important feature about what can happen in these sort of things. So note that the left-hand side, this just means left-hand side, this is divisible by 3. I mean, 3 is relevant because it's the GCD, so I'll just point that out. It's the GCD of 6 and 15. Okay, but 3 does not divide 10. So that means you have a massive problem, and this is never going to work. So there are no integers. So there are no integer solutions to this equation. Okay, so this is something to watch out for. Now, okay, so that kind of thing, we'll state this as a result later, but it's going to become a thing, right? Where, right, so when you look at what the GCD of the coefficients is, the left-hand side will be a multiple of that number, so the right-hand side must be a multiple of that number for a solution to exist. Okay, it wasn't really a problem over with this example where they were relatively prime because the GCD was 1, and any integer you put over here is divisible by 1. So it's something you have to watch out for if you have coefficients that are not relatively prime. So anyway, it's worth taking a second just to process what would be happening, I guess, geometrically. Geometrically, if you like to think about the plane and lines and so on, but when you have something like the graph of ax plus by equals c. This is a line in the plane. So, I mean, thinking of x and y as real variables, all the real x, y's make a line. And the point is we are asking if this line goes through points on the integer lattice, is what we would say. If this line goes through points on what's called the integer lattice. I mean, that's just a fancy way of saying the points in the plane that have coordinates that are both integers. So, think of the Cartesian plane. The integer lattice is, a bunch of points that look like this. Okay, they go all around. I'm not going to draw them all, but hey, points like this. And what happens is, when you graph a line, and I mean this one, I could try to make a lazy graph of this, but if I was going to graph this, this is something like y is, I think it's this. You solve that equation for y, I think it looks something like that. And yeah, so anyway, what happens is you've got some kind of line, which I'm not going to make a perfect picture, but it should be avoiding all the points that you draw, right? Okay, so it's some kind of line where it goes through, yes, y-intercept, well, I guess 2/3, slope minus 2/5. And if you plot it with the integer lattice on top, what you would see is that line just never hits any of those points. It's always missing them. Okay. But anyway, in examples like this, it would actually be going through some of them. Okay, so anyway, we've seen most of the important things so far for this topic. We've seen like a technique for producing solutions when they exist. And we've seen a scenario that we're starting to understand how to identify where solutions don't exist. I guess the thing we haven't discussed yet is when you know a solution exists, like how do you find more than just one? So we'll get to that. But let's build on this fact, or this idea first. So here's a theorem. Actually, it's a big, massive two-part theorem. It's like two theorems. It's going to give us the whole story. So we're going to assume A, B, C are integers. And I mean, we're going to look at an AX plus BY equals C. We don't want A and B to both be 0 because that's silly. So we're going to assume at least one of A and B is non-zero. Okay, there is the equation. This has a 0 left-hand side if they're both 0, and it's not worth talking about. But this is the assumption you need to have a GCD also. So anyway, let's also let D denote the GCD of A and B. Okay, so we kind of are seeing that might play a role based on what we were doing over there. So first statement is that the equation, the Diophantine equation, which is AX plus BY equals C. This is going to have integer solutions. It has integer solutions for x and y. This will happen if and only if this GCD is a divisor of the right-hand side. Okay, that's the thing we were seeing was not true in this example. And so that's led to having no solutions. But if it is, this is also saying that if it is in fact, if the right-hand side C is in fact a multiple of D, then solutions will exist. So we'll prove that. And then the extra bit here, which is saying a lot more, This is this thing we haven't really seen yet, but if it has solutions, it actually has infinitely many solutions. So if it has a solution, remember we were talking about solutions, or I may not keep writing it, but I do need it. Like we're talking about integer solutions. But if it has an integer solution, then in fact it has infinitely many. And there's a recipe for making them. Okay, and so if you know one, so if let's say we know one solution, and let's call it x naught, y naught. Okay, if that's one pair that satisfies the Diophantine equation. So if this is any one particular solution that you happen to know. Then the general solution, which is supposed to be describing all possible solutions, is given by the following formula, which says that the x's are going to look like the x naught you knew about plus b over d times something called t here, and y is the y naught you knew about minus a over d times t. And what t here is supposed to be some kind of parameter, but it's an integer. It's like it could be any integer. So t is an integer. Okay, so if you consider every pair you get from all the possible integers t, that is the family of solutions. That's what this is asserting. Okay. So we're going to prove all this stuff, right? So we didn't prove it yet, but we will. And in terms of using it, we can think about that for a second. But this, one of our goals is to describe all the solutions to one of these linear Diophantine equations. And so statement 2 here is pretty much setting up the recipe for you, right? It's saying if you want to describe all the solutions, you want, write this down basically. But what you need here is to know one solution. Any one will do. Okay, you have to get your hands on one solution to the problem. And then once you have one solution on hand, you just write this down, basically, and it describes them all. Okay. So back when we were doing some examples earlier, and we actually found, a certain solution using the extended Euclidean algorithm, that we're going to feed into this, and then that'll help us describe all the solutions. So before we jump into proving anything like this, I'll just try to illustrate this. So just as an example, we had this example, we found one solution to this, which was, we wrote it on the board earlier, it was 18 and 48, so x naught, y naught is, 18 and negative 48. We found that from our extended Euclidean algorithm, multiplied both sides by 6. Okay, and so once you have that, we should be able to describe all the solutions of this equation. Okay, so anyway, let's just note a couple things. First of all, the a here, a is 19, b is 7, and d, the GCD is 1. Okay, and those are the things that will get fed into this thing down here. Okay, so the general solution are going to have the following form. Right, so x is going to look like what it says. It's x naught plus b over d times t. So x naught is 18, and d is 1, right, in our example. Right, so b is 7. And then y would be given by the y naught we know, which is minus 48. Minus a over d times t. Okay, a is 19 and d again is 1. So that's what the formula looks like, where again t is an integer. So this is describing an infinite family of solutions, so it's maybe worthwhile to imagine listing them just to make them feel real. So you can list them if you like. What I just mean is just make a small table just to see a couple of them. We're obviously not going to list them all because there's infinitely many of them. But I mean, you could think about plugging in different t's. You know, for example, if I was to plug in t equals 0, that gives me the original one I knew about, which is this one we knew about. This is somewhere in our table. If t is 0, that's what you get. If t is 1, you could plug that in and see what happens. This is the second solution. You know, 18 plus 7 is 25, and minus 48 minus 19 is something. Okay, I mean, you could list more. This is the point. And you start going this way, what's happening with our thing is the numbers are sort of growing. Like this is something like that. If you weren't satisfied with the size of the numbers we had in 0, you can see we can get a better one if we go this way. We can get one, by better, I mean we can get one with smaller coordinates. Anyway, if you go this way, if you want to plug in t equals minus 1, this will give you 11 and minus, what, 29? Okay, if you go this way, even more. You know, you can get what, this is 4 and maybe 10? Okay, and so on. So there was nothing, by the way, particularly special about the solution we found. And it's one among this list. But once you find any one solution at all, then it wouldn't really matter which one you start with. But once you find any one solution to this problem, you can list them all in this way. You'll always get the same list. Okay, so that's how it would work. Okay. And we're going to start proving the theorem, I guess, but the example makes sense. And if, you know, yeah, if you actually have a non-trivial GCD, this coefficient gets cut down a bit when it's divided by that thing. So let's start proving this. The first part, in essence, we should know how to prove. The second part takes a little more effort. The reason why I'm saying we should know how to prove the first part is because the ideas that go into it are the same ideas that went into our examples so far. So as far as this first part goes, so we're going to do theorem 1 right now. Just focus on part 1. Okay, so this is an if and only if statement, which means we have two things to prove. Right? An if and only if is, you know, that's like a two-directional implication, right? So we have to prove, you know, the left thing implies the right thing, and the right thing implies the left thing. So split it up into two proofs. Okay, so let's start with this one. So what's on the left side of the if and only if is the assertion that this thing has integer solutions. Now, when we say it has integer solutions, that really says, what it really means anyway, is that an integer solution exists. There's at least one. Okay, so that's really an existence statement. There's at least one solution. So let's start out with that. Suppose there exist integers, x and y. With the property that ax plus by really does equal c. Okay, and the point is that the left-hand side is a linear combination of a and b. So since we know that D, the GCD, divides A and also B, so D we set up here, right? That's what D means. It's the GCD of A and B. It's a divisor of both A and B. So D also divides the linear combination which is ax plus by. Okay. That was an old fact we proved very early on, that any common divisor of A and B divides any linear combination of A and B. So anyway, that is C. Okay, so we're done. Right, so AX plus BY is C. So that establishes that D divides C, which is what is on the other side of the if and only if. Right, so we prove that this assertion implies that assertion. Now we have to do the reverse. Okay, so now we have to prove the backwards implication of the if and only if. So here the starting point is to assume that the GCD divides C. So we'll suppose that D divides the GCD, which is D, divides the right-hand side C. And that lets us do the following. Right, so we could write, I guess, C as DE, or some integer E. Okay, but let's pause for a second, because even if we don't realize it, we actually know how to prove this. Okay, what are we trying to prove is that we're trying to prove that a solution exists to this equation. Okay? So this is supposed to be like our examples, right? How did we actually find a solution to our examples? Was we invoked the extended Euclidean algorithm to get the GCD written as a linear combination of A and B. And then perhaps we needed to scale up the equation by multiplying both sides by something to make it work. And this assumption here is going to make the scaling work out for us. Okay, so let's walk through it. So we want to use the extended Euclidean algorithm. Okay, so by the extended Euclidean algorithm, I'm going to say, I'm not going to call them X and Y to not get confused here. Let me just give them different names. But there exist integers. We just call them U and V, just to use different letters. The point is you can write the GCD, which is D, as a linear combination of A and B. Okay, and then the point was that we don't actually want D on the right-hand side. We want C on the right-hand side of such an equation. And so this is like when we scale it up to get the right number here. The thing is, if you want to get C, but you had a D, you just multiply both sides by whatever that integer E was. Okay, so multiply both sides of the equation by E. Okay, and so what happens then is you would have A times UE plus B times VE is equal to DE. And the point being, DE is actually C, the original C. Okay, and so we're able to do this with an integer E. So E is an integer like 6 and not something like 10 thirds, like in that other failed example. Right, so since E is an integer, we're certain that this parentheses expression here is an integer, and so is that one, right? Because U, V, and E are all integers. Okay, so anyway, this shows. What this shows for us is that the pair, which is x being UE, y being VE, is a solution to the equation that we're trying to show has solutions. Right? So we actually found one. We explained how to find one. If you find the U and V from an extended Euclidean algorithm, multiply them by whatever that E was, which was an integer, and that actually produces a solution, so that proves the equation has solutions because we found one. Okay, it's the same way you would actually find it in practice, like we did in our example. Okay, so that wraps up statement 1 over here. Okay, which is just all about classifying whether or not solutions exist. Okay, and then that still leaves statement 2 for us that we have to work on. You okay with statement 1? Okay, again, the ideas in this proof are supposed to be the same ideas that we talked about in those examples, sort of translated to general arguments. Okay, so anyway, the rest of it's a little, takes a little bit of effort. Okay, and I'm going to try to reduce it to a simpler case. Okay, so let's, we do need to tackle statement 2, but before we proceed with it, proceed with statement 2 here, let's consider a simplified case. So this is what you would call the homogeneous case. So if you were to consider the type of Diophantine equation where you have a 0 on the right. Okay, so that, I mean, is one example of a Diophantine equation where C is 0. That can be studied. It's a special case. We're going to prove this result for the special case in a second. And then the idea is to reduce the general case to the special case. Okay, so we're going to focus on the special case first because we're going to leverage that to prove the general case. Okay, so this will be a little simpler. I mean, you can think, what is this going to say before we dive in here? What would statement 2 actually look like if C was 0? Right? Right, here's your equation. So imagine if, I mean, it's over there too. But if C is 0, just to point something out to you that's kind of obvious, I guess, is that 0, 0 is a solution. Right, so in this example, 0, 0 is a solution. Solutions definitely exist. And if you believe this is true, then you can use 0, 0 as your x naught, y naught. So the solution set should just look like basically b over d times t, comma, minus a over d times t. So we'll prove that here. Okay, and so we'll just have this be a little intermediate lemma. So suppose we have integers a and b. Suppose they're not both 0. In this course, we might get lazy about pointing out that things are meant to be integers because the whole context was always about integers. But so I hope that's okay. But if you're ever confused, you can ask. But anyway, a and b are integers, not both 0. And first statement is just an even further special case. If you had relatively prime integers, so if the GCD of a and b is 1, then every solution to ax plus by equals 0 is going to have the form which is, it's like what's written over there where x naught, y naught are 0 and d is 1, so it's really simplified. So x is bt, y is negative at for some integer t. Okay, and then we're going to build on that. And I think I'm going to say goodbye to this. I don't think we're going to wrap up this whole thing today, but let's wrap up at least this lemma. There's a second statement to this lemma, which is to back off of the relatively prime assumption. So what if they're not relatively prime? So this statement is in general. So let's say if D is the GCD of A and B, which is not necessarily 1 here, then every solution to this homogeneous problem, ax plus by equals 0, has the form which is x is bt, y is negative at for some integer t. Oh, sorry, I forgot to actually state it. say over b. And that's what the harder theorem we're trying to prove would say is true here. And we'll establish it in this case first. Okay, so anyway, let's start out with we have this lemma now that's in two parts. We're going to start with part one. This is lemma part one. It's written over there. Okay, so we're going to assume the GCD of A and B is 1. We're assuming they're not both 0. And I mean, actually one of them can be 0, and everything we've been saying is still true. So we might be a little careful about how we treat that. But what we'll say to start with is, since they're not both 0, one of them has to be non-zero. And they really play symmetric roles in this discussion, like A and B are kind of interchangeable. So we could just assume one of them is non-zero. So what people might say is, without loss of generality, which is often abbreviated like this, let's assume B is not 0. Okay, so I mean, it could be the case that B was 0 and A is non-zero, but then you just relabel them and call the non-zero one B. That's the rough meaning of this. So anyway, now what we want to do is show that all the solutions of this equation have this particular form. So we'll suppose we have a solution. So suppose we have integers x and y. Suppose we are given integers x and y, which have the property that a times x plus b times y is equal to 0. So that is to say, suppose we have been handed a solution of this equation. What we're aiming to do is to show that it has this certain form, given below. So we have to figure out why that is. Okay, so it follows then from this equation that we know to be true here, we can rearrange it. So rearranging the equation, you could write this as saying that a times x is negative b times y. Okay, and what that shows us, something kind of significant, it shows us that this left-hand side is divisible by b. Because look, it's a multiple of b. Right, so and so b divides ax. That's certainly follows, right? Because the a times x is b times another integer. So what you get from this then now is where we're going to lean on something we proved earlier, which is a pretty useful and important result. Okay, so we did make this assumption, and maybe I should have emphasized it in this proof, but in statement 1, it is assumed that the GCD of A and B is 1, right? So we're assuming A and B are relatively prime. Okay, so here, A and B are relatively prime integers, and you know B divides this product of A with something else. Okay, and so we had this result from a couple classes ago that said if A and B are relatively prime, but B divides the product of A with something else, then B is going to have to divide the other thing. Okay, so let's write this. Okay, so since the GCD of A and B is assumed to be 1 here, it follows from, and I'll give you the reference if you want to just remember and look it up, but it follows from proposition 216 that it must be the case that B divides X. Right, so B and A are relatively prime, so B must fully divide X. We proved that in the past. And that's kind of what we need, because what we're really asserting over here is that X is a multiple of B. Which multiple is it? We don't care. It's just times some t, but it's some multiple of B. And so this is going to give us pretty much what we want, at least half of it. So what this means is that X has the form B times t for some integer t. then furthermore, just building on what we have over here with this equation. So further, so this tells us about x. We want to know something about y. So let's look at the y over here. So b times y from this equation is minus ax. Right? And now we know that x is bt. So this is minus abt. Or inserting the x equation into that. So now you can just divide both sides by b, which we do know is not zero, by the way, as we said it earlier. So dividing by b. Dividing this left and this right by b gives us that y is minus at. That's as desired, right? So we've shown that x has to have the form b times t, and y has to have the form minus a times t. Okay, so there it is. Okay. So that was statement one. Let's just build off it and do statement two. Statement two is supposed to follow fast from this special case. So for statement two, see if we can finish it. So suppose D is the GCD. Suppose D is the GCD of A and B, and here we're given a solution to AX plus BY equals 0. Right, so an X comma Y satisfies the equation that A times X plus BY equals 0. Okay, so in this case, D is the GCD of A and B. It divides evenly into both A and B. So you could divide both sides of this equation by D, and that would be okay. Right, so dividing by D So if you divide both sides of this equation by D, the point is that D divides evenly into A, so that is an integer. And D divides evenly into B, so this is also an integer. And 0 divided by D is 0. Okay, so what's going on here is, so note that A over D and B over D are relatively prime integers. Okay, this is something we proved in the past too, that if you have a pair of not relatively prime integers and divide by their GCD, you get relatively prime integers. And then we can just hit it with statement one. So by statement one, which we just proved, well, first of all, xy satisfy this thing, where the coefficients are relatively prime integers. So you could say by statement one, what must be true is that x has to be this coefficient times t, and y has to be the other coefficient times t for some integer t. Okay, we just run out of time, so I would like to let you go. But I just want to point out we've basically manipulated the equation into one that has relatively prime coefficients, and then just applied the result we just proved to that one that has relatively prime coefficients, just to get the thing we wanted. So out of the box, and that finishes this lemma. And then next time we could use the lemma just to finish this discussion and prove the most general fact about